Hi everyone! What you are seeing in the background now isn't a typical shader for which I usually create tutorials here. This time I took a little detour and I'm presenting the first sky shader in Godot Engine on this channel. Since it's a pretty handy effect that we might use in our next game, I'll show you how such a sky shader works. Let's get started. Before I begin, allow me to give a small shout out to our game Whispers of Prague. It's a point-and-click adventure game created in Godot 4.2.2 and at the time of recording this video, it's been out for about 10 days. During this time, we've received many positive reviews and useful feedback, which will serve as inspiration for our future projects. We released the game on Steam for $10, so if you enjoy adventure games with lots of text, or if you just like to support the creation of more tutorials on this channel, please consider purchasing it. We are deeply grateful to everyone who does so. Now, finally to the topic of this video. The sky shader differs from other types of shaders in that we don't apply it to a canvas item or mesh instance 3D, but to world environment. It's essentially a dynamic skybox that we'll see all around us in our 3D scene. So, this is my third-person controller project, and I'll open the world environment node of it in the inspector. Let's find it. Here it is, and the inspector. So now we have a standard sky environment, which is not what we need now. Let's change it. Sky will remain, but let's click sky, and instead of physical sky, I will use, let's see, a new shader material. Okay, click it, and we need a new shader, which is now mode sky, and let's call it, for example, I don't know, planet. We will use some planet, as we could have seen at the beginning of the video. Okay, everything else can stay as it is. Let's create and click it again to open in the editor. So, as we can see, the sky shader has a shader type sky and has only one method, sky. Let's start with the sky background by creating a uniform parameter and then inserting a texture into it. I'll just expand the editor a little bit, and now the uniform parameter, uniform sampler 2D, sky text for sky texture, and it will be source color and filter linear and hint default black. Okay, I'll expand it shortly, and now we need to use this texture to define the sky color. Color equals texture of this sky text, and instead of UV coordinates we are using sky coords. This is different. And RGB. That's it. We should still see the black color right here. And now in the inspector I will use a prepared texture that we created using a free tool called Space. You can download it from the author website, which I link in the video description. So let's expand shader parameters, and to sky text I will drag sky PNG here, and yeah, we can see something. Let's start the application, and we should see there, but it seems the floor gets in the way, so I will disable it for the time being. Where it is? Here, static body 3D, and it's gone. Cool. Let's get back to the shader code. Okay, note that color is vector 3 in this case, as the sky shader does not use an alpha channel. That's why we are using the RGB suffix right here. By the way, the documentation states that the sky function can be called up to 6 times per frame, which could be too demanding on performance in the case of complex calculations. Therefore, we'll enhance our code with the following condition, which is also based on documentation, as you can see right now. Let's do it. If at CubeMat pass, let's just simply assign a constant color, vector 3, something like 0.2, 0.6, and 1, as the documentation suggests. Else, let's do our original calculation. And here it is. By the way, I used filter linear because we want something like a smooth transition between pixels of the sky image, and we want to avoid any unwanted pixelation because it's definitely better for the sky. And in default bike, I think it's clear, if there is no texture, we will show a black color. Okay, now it's time to add more objects, starting with the sun, which doesn't need a texture because we'll generate it with a simple calculation. First, I'll add a uniform parameter to determine its position in 3D space. So that would be uniform vector 3, because we are in the space. And then let's call it sun pos, and the default value let's put to the origin, so it's vector 3, 0, 0, 0. Now let's calculate the sun. We'll need the dot product between the vector from the camera to the center of the sun and the vector from the camera to the current pixel on the screen. We will use internal variables idea, which is the direction from camera to the pixel, and position, which is the position of the camera. And since the idea is already normalized, we'll need to normalize sun pos minus position as well. Let's do it. So I think we need to do that right here. Float, let's call it ds, direction to the sun, and dot product, as I said, between the normalized vector sun pos minus position, which is basically the direction from our camera to the center of the sun, and the second vector is idea, the direction from a camera to the current pixel we are calculating at this moment. Okay, and we'll use the result to modify the final color of the pixel. We know that the larger the angle between the vectors, the smaller their dot product becomes. And for vectors that are perpendicular to each other, it equals 0. Therefore, we'll use the value of ds to calculate the RGB components, and we'll square the resulting vector to make the sun shine brightly at its center, with the brightness gradually decreasing towards the edges, like this. Color is increased by power. It will be to the power of 2, which is the squaring I was talking about, and then our vector 3 for the 3 color components. Again, the power of ds to the power of 40. Now I think I can copy and paste because we will use it 3 times in a row. This part, first, second, and third, and the vector is to the power of vector 3, 2, 2, 2, and of course the coefficients should be different, so it's 40, 60, and 100 to give some nice color to the sun. Can you see it right here? Of course, if we wanted a star of a different color, we would have to change these values. But we are satisfied with this. However, something is wrong because it looks like half of the sky has turned black. This is because the dot product can also be a negative number, so the subsequent sum can go below 0. We'll fix this by setting 0 as the minimum allowed value. So let's use this maximum of this dot product and 0. So it's never below 0. Okay, and now seems to be fixed. Yeah, sky is everywhere and the sun is in the center. Now it's all set. There is just one more problem. As we can see, our character and the sun share the same position at the origin of the coordinates. So the character is standing right in the sun. Let's move the sun a large distance away so that it nicely illuminates the planet later. In the inspector, let's find the parameter. It should be here, sun pos, and use this 20,000, 0 and negative 10,000. Now it's better. Let's try to execute. Okay, here's the sun, here's our character, and we'll place the planet somewhere behind the character. Okay. We are done with the sun and we'll move on to the planet. For it, I downloaded a texture from the following website, which is an excellent resource of quality textures of the solar system. And again, I added a link to the video description. So now we need a new uniform parameter. I'll add it and later I'll drag the mentioned texture into it. Note that I will use the filter linear again, so I would ensure smooth color transitions without unnecessary pixelation. Let's do it. Uniform sampler 2D, let's call it planet text, and again source color and filter linear. This time it's not necessary to use default black because I definitely don't intend to use a planet without a texture. Okay, rendering the planet won't be as straightforward as with the sun. We want it to rotate slowly, then to make the sun illuminate the correct half of the planet, and later we'll add clouds and shadow of the moon. For this, we'll first need a few helper functions. So let's get started on those. We'll start with a structure that we'll need for the upcoming calculations. I think this is the first time I've used a struct in a shader, and it is a variable that contains several other variables of different types. We'll name ours ray hit because it will be needed for the intersection of a ray with individual objects, in this case with the surface of the planet. So struct ray hit, and let's define it. It would contain boolean is hit, which is true if the ray made an intersection with the object, or false if not. Then vector3 normal, that would be a normal vector at the point of intersection, and finally vec3 hit point, which is just the mentioned point of intersection. And now the function, which I will call hit sphere, and will use it at least twice, since both the planet and the moon will have a spherical shape. The function will return a ray hit structure, this one, with information on whether the ray intersected with the sphere, at which point intersection occurred, and the corresponding normal vector, which will be needed later for the lighting calculation. By the way, there is a great site which in details explains how to calculate an intersection of a ray and a sphere. I found all necessary informations on this one, which I'm showing right now, and the text clearly explains how it works. Again, I will add a link to the video description. So let's implement it in our function as well. Okay, let's do it. The function will be a bit longer, but I'll try to explain it in as many details as possible. And let's expand it so we can see more of the code. Very well, so as I said, we will return array hit, the structure, and the function name is hit sphere with parameters vec3, that would be array origin, then vec3 radius direction, so we know from which point we start and in which direction we continue our calculation. Then we need the sphere to calculate with, and the sphere has a center and a radius. Float sphere radius. Is it correct? Yeah. Okay. That's all parameters we need. And now, first we'll define the array hit variable array hit, which will finally return hit. Okay, now it's correct. And now let's start with defining the parameter is hit, which should be false at the beginning. I think it's probably not necessary, because this should have the value false by default, but it's better to be sure. Okay, and now we need the direction from camera to the sphere center. Let's call it OC, and ray origin minus sphere center. Okay, and now, as we could have seen in the article I showed, we need to solve a quadratic equation with these coefficients. Float A is dot product of radius and radius. Float B would be 2 multiplied by dot product of OC and radius, and finally C is dot product OC minus sphere radius by sphere radius, so to the power of 2. Okay, and now the solution. So we need to define delta or discriminant of this quadratic equation, which is, as we know from the math, is b to the power of 2 minus 4ac. Okay, and now we'll need to make a square root, but as we know, a square root is defined only for numbers greater than 0. So if delta is less than 0, there is nothing to calculate, nothing was hit, so we return return the current array hit, which contains nothing. There is no hit on the sphere. Or we can continue. Float root as a square root would be square root of the delta, and the actual solution of the quadratic equation is this one. There are two solutions. T1 would be minus b minus root divided by 2 twice a, and similarly T2 is minus b plus root. Okay, I guess we all know that from the high school or other schools where we were taught the quadratic equations, and now we are interested only in the closer intersection, because the other one is on the other side of the sphere and it's not visible. So let's find out which one it is. Float t near is the minimum value of these t1 and t2, and similarly float dfar would be the maximum of t1 and t2. Okay, and now again we want only a positive number or a 0. So if t near is a negative number, we want to consider the other one in this case, but only if t far is greater or equal to 0, then let's define t near as 0. Okay, else we just return again the empty ray hit. Again, there was no hit we are interested in. Okay, so now we have the t near value, and we can get the normal vector at this intersection point. And to make the calculation a bit faster, let's use a GLSL function called FMA, which, as we can see now in the documentation, is the multiplication of first two arguments and addition of the third one. So ray hit normal vector would be hit point. Now we are calculating the hit point. I am just talking too fast. FMA of radier, then t near, but we need a vector 3 to compare them, and finally ray origin. Okay, so we take the ray from the origin and then add a multiplication of these two values to get the exact point of the intersection. Okay, and now the normal vector. The normal vector is perpendicular to the corresponding face, and for sphere it is the calculation is easy because it always equals to the vector that connects the center with the point of intersection between the ray and the surface. So ray hit normal would be, as I said, and we are interested only in the direction, so we'll normalize the vector. Normalize, and as I said, ray hit point minus sphere center. Great. And at this point we know that we had some hit, so let's set it. Ray hit is a hit is true, and this is it. This is the function. So that was the first one, and now we'll need to recalculate the UV coordinates for a specific point on the sphere to ensure the texture is displayed correctly, because if we want to display it on a sphere, it is definitely not the same than displaying just on a plane. So for this we'll use another well-known formula which we can find on Wikipedia if needed, and the function would be called get spherical UV. Vector 2 get spherical UV, and the parameters are vector 3 point on sphere, and we also need a rotation because we already know that the planet will slowly rotate, so it's necessary to calculate this shift into the calculation. Okay, and now let's find the normalized vector of this point on sphere, because again we will work with normalized vectors. Point on sphere, all right, and we need to calculate the azimuth and zenith, which is very similar to longitude and latitude on Earth. Let's do it, and it is usually called theta and phi. Theta or or is it phi? I'm not sure. Let's see, a tan nz and nx. Okay, and so it is angle around the y-axis, something like the longitude, and float phi is a cos, inverse function to the cosine of n dot y. That would be angle from the pole or a latitude. Okay, and as I said, we need to add the rotation angle that will change over time. So theta would be increased by the rotation. Very well. And now finally the UV calculation. So float u would be theta plus pi divided by tau, which is twice pi. Basically, we normalize this value to the range from 0 to 1, and let's do the same for the v. Float v would be phi divided by pi, again normalized on the range from 0 to 1. And finally, we will return vector 2 of u and v. Great. Okay, almost there. Now the final function, which we'll use to calculate the lighting of a pixel based on the given normal vector and the direction from the light source. Once again, we'll use the dot product because we know that the more a surface is tilted away from the light ray, the less light it reflects. Let's do it here. Vector 3, this is the last one I promised, and after that we'll finally create a planet. Compute lighting with parameters vector 3 normal and vector 3 light, there, direction from the sun. And we'll simply return this. Return vector 3, that would be, again, we need to return only positive numbers or zeros, so it would be max of dot normal and negative light there, because we are interested in a reflected light which has an opposite direction than the light emitted from the sun, and 0. Okay, great. By the way, when we run the scene, we'll see, let's do it, we will see that our character is illuminated by the skybox. Can you see how it has some kind of bluish tint? And this is probably we don't want. The solution is to disable ambient and reflected light in the environment settings, and it should be here, ambient light and reflected light. So now it's taken from background. Let's disable it both, and let's try it again. This is perfect. Now it doesn't react to the skybox and it's just shown as it's supposed to. Cool. Okay, so now, as I said, the character looks more natural, and it would look even better with some floating animation, not just standing there, but that's not the focus of this tutorial. Okay, so we can start with the planet, and to allow us to modify it later, we'll define its radius as a new uniform parameter. I'll do it here. So uniform float planet radius, and let's start at 300. It doesn't mean it would have 300 in diameter, but it is just something that worked pretty well for me. So no, okay, now the code. I'll start with the position of the planet, which will place at a reasonable distance from the origin based on the current radius, somewhere at this position. Then, using the hitSphere function, we'll determine whether the current pixel belongs to the planet or to the surrounding sky, and branch the code accordingly, like this. So let's find the sky function, and we are working in this branch. Okay, and we'll do it after this calculation of the sum. So Is that correct? No, I don't think so. The planet can cover the sun, of course, so we'll do it before that. Very important. Vector 3, planet center would be, let's define something, and again we could later modify that with new uniform parameters, but right now let's do it this way, -100, and let's use the planet radius. Planet radius multiplied by 2. Okay, and now, as I said, we'll need the hit sphere function to determine if the current ray hit the planet, and the planet surface should be displayed. So, ray hit, planet hit is the result of hit sphere function with current position of the camera. I there is the direction from the camera to the current pixel, and we are interested in planet center and planet radius. We define the sphere used in this function. Okay, and now if planet hit is hit, then display the planet, else display the sun or the rest of the sky. Okay, let me just fix the indentation. Can you see something? There we go, we have a planet. Let's start the application. Yeah, it currently looks like a black hole. At least we can see that the calculation correctly identified where to display something other than the skybox. Now we'll apply the texture to the planet using spherical coordinates, for which we will use the getSphericalUV function. Let's do it. So if planet is hit, nothing is here yet, let's fix it. Vector 2 UV would be the result of getSphericalUV, and we are interested in the planet hit point and minus planet center, and the planet should rotate. So let's try time multiplied by 0.02. Again, we can define the speed of the rotation in shader parameters. Right now, let's do it this way. And finally, the texture. So the color would be texture of the planet text and UV and RGB component. Okay, yeah, something is wrong. Of course, we don't have the texture in there. So in the inspector, let's find the parameter here, planet text, and drag planet PNG into that. Is that okay? Re-importing assets. Why is that, and where did it go? I mistakenly put it here for some reason, so let me fix that and do it again. Now dragging. Shit, where are the parameters? Expand again. You know, sometimes Godot is it's still a great engine, of course. Now here we go. That's better. Let's see how it looks if we run the scene. A nice result. You can see that the planet is currently ignoring the sun, and it's evenly lit across its entire surface. We'll fix it right away. We'll again use the hit sphere function again, but this time we'll calculate the direction of the ray from the sun, not from the camera as before. Then we'll apply the compute lighting function to get the correct shade of the pixel color. So after the planet texture, we will fix the lighting. So vector 3, so let's call it sunlight direction there is, it's direction, so we are normalizing the vector planet hit, and it's a hit point minus sun position. So we are getting the vector from the sun to the planet, and the result of the hit sphere would be again the ray hit structure, and this time we'll call it light hit, and it would be a hit sphere with parameters planet hit point again. Now negative sunlight direction, because again we'll be using the reflected light, planet center and planet radius, here. Okay, so this is the light hit, and now we need to calculate the actual lighting, which is again vector 3 lighting, and it is the result of the function compute lighting with parameters. And now we need a normal vector, so planet hit normal, which we already calculated in this function, hit sphere, and sunlight there. All right, and now of course we need to use that to recalculate the color, and we'll simply multiply the color by the lighting value. Okay, let's take a look. Very nice planet. Alright, I would say the video is already quite long, and it's probably better to absorb the new information first before tackling the remaining tasks. So I'll wrap it up here, and in the next episode we'll add clouds above the planet's surface and a moon orbiting around it. Thanks for watching, and I hope this type of shader has intrigued you as much as it has me. You can do amazing things with a sky shader, like simulating day and night cycles, including sunrise and sunset, the sun's position throughout the day, dynamic clouds, or the moon's phases during the night. But we'll save that for future tutorials. For now, take care, best of luck with your projects, and I'll see you in the next video.